Hi there. This video discusses the concept of Mealy machines, which are basically an extension of finite automata. Now, the normal finite automata that we know, deterministic finite automata, non-deterministic finite automata, they basically accept languages. But the purpose of Moore and Mealy machines is different. It's to convert an input to an output. And an application of this is in the area of NLP, where transducers are used to convert, for example, one word to another, like in the case of spell check. Okay, so let's get along and see examples of Moore and Mealy machines. So here's first of all a simple example to show how we can complement a binary number using Moore machine, right? So Moore machine, the difference it has from a DFA is that there is an output associated with each state, right? So, and as usual, the transitions are there, like for a DFA, but the only difference is, for a particular state, there is some emission of output. Okay. So this is a Moore machine in order to complement a binary number. So the Q0 state represents the state in which the output should be a 0. So that would happen whenever the last input symbol is a 1, right? So whenever you have a 1 input, we go to Q0 state, right? And from Q0 state, if we get a 1 input, we remain in Q0 state and we emit 0. Okay, so basically what's happening, whenever we get a 1, we go to Q0 state and we emit a 0. So in effect, it's complementing the binary 1. And Q1 state is the state in which a 1 is emitted. So a 1 should be emitted whenever we get a 0. So you see that all transitions on 0 go to Q1, and in Q1 state a 1 is emitted. So whenever we get a 0, we go to Q1 state and we emit a 1, and that's the complementation for a binary 0. And so this machine, this automaton, it shows you how to complement a binary number. This is a Moore machine. And now let's go on to a related machine called a Mealy machine. Now the difference here from Moore machine, in Moore machine the output symbol is associated with a state, right? But in Mealy machine the output is associated with, for example, every transition, right? So for a particular state on a particular input, you get a particular output. Okay, so it's just like your transition function, except that this is an output transition function. So for normal DFAs, depending on a particular state and given the next input symbol, you go to a new state, right? But here what happens, you have the normal transition function for going from one state to another, and you also have the output transition, which basically says that for a particular state on a particular input you go to a particular output, and it is indicated by this second symbol here on every transition, right? And I mean this example has single state, right? But Mealy machines, there's no restriction on the numbers of states. You could have many states, right? Just like a Moore machine, just like a DFA, NFA. So now let's just look at this example for complementing a binary number. So you just have a single state Q0, and whenever you get a 0, you output a 1, and whenever you get a 1, you output a 0, and you go back to Q0. There is no need of a second state. Okay, so this is in short how the Moore and Mealy machine works. Let's look at more examples. Let's look at the next example I'm going to show you is to identify the occurrences of AFA, ABA in a given input string. Okay, so you have a string of A's and B's. The problem is whenever you get an ABA, whenever you see an ABA substring, you have to emit a 1, otherwise you have to emit a 0. Okay, so and based on the number of ones you get, a program could potentially sum up the ones and get the count of the number of occurrences, right? So let's see Moore and Mealy machines for that. Okay, so the DFA would start off from Q0, and here Q0, let's see what Q0, Q1, Q2, Q3 stand for, right? So Q0 stands for the state in which no portion of this ABA string has been generated in the end. Okay, and Q1 stands for the state in which only the A of the terminating ABA string has been found, right? The first A. And Q2 corresponds to the state when the AB of the terminating ABA has been detected. And Q3 stands for the case when the terminating ABA, the entire ABA has been found at the terminating the string. Okay, so let's start off here. Q0 is when nothing has been found. So Q0 could happen when you get a B, right? So whenever you get a B, you go back to Q0. No portion of ABA has been generated. And I will come back to the zeros and ones later. So when you get an A from Q0, you have obtained the first A symbol. So you go to Q1. And in Q1, if you keep on getting as many A's as you want, it still means that you have obtained only the first A of the terminating ABA. And from Q1, if you get a B, then it means you have encountered the AB from the terminating ABA. So you would go to Q2, right? And from Q2, if you get a B, meaning you have received an ABB in the end, then it means that now you have obtained no portion of ABA, because ABB, if you take ABB, then you don't have an A in the end, you don't have an AB in the end, and you don't have an ABA also in the end. So no portion of this ABA has been obtained if you have ABB. So you go back to Q0. Okay, and from Q2, if you get an A, meaning you obtain the ABA string, then you go to Q3. Okay, and so you would notice that all these states have a 0, meaning that ABA has not been encountered as the terminating string. Okay, but Q3 only has a 1, because in Q3 it means that this entire ABA has been detected in the end of the string. Okay, all right. And what about Q3? From Q3, if you get a B, then actually you have obtained an AB in the end, so you have to go back to Q2. Okay, and if you get an A from Q3, you have to go all the way back to Q1, because you have encountered A, the first input of the terminating of the ABA. Okay, so this is your Moore machine. And now let's write down the Mealy machine. The Mealy machine also happens to be exactly the same in this case, right? So actually, in some of the cases, the Mealy machine is exactly like your Moore machine. And in this video clip, we will also learn when that happens. So how would you convert this Moore machine to a Mealy machine? See here on input A, you're going from Q0 to Q1 and emitting a 0. So you could as well take the 0 and put it here, right? Because I mean, that's what you're doing. You're saying that from Q0 on input A, you have to go to Q1 and you also have to emit 0. So why not take 0 and put it here, right? So we can do the same for all the states, right? You take the 0 and put it here, you take the 1 and put it here, you take the 0 and put it here, right? And you take the 0 and put it here, 0 and put it there, take the 0 and put it there, right? And you'll get this Mealy machine, right? So so at least sometimes a Moore machine can be easily converted to a Mealy machine, okay? Or it's actually a Mealy machine that can be easily converted to a Moore machine. Okay, let's look at that. Let's look at that a while later. Now here I have another example. You want to find out, you want to detect, given a binary string, you want to detect the residue, meaning the remainder mod 3 for each binary string encoding a binary integer. Okay, so basically the idea behind this is you keep on adding binary digits in the end, zeros and ones, right? And for each addition of a binary digit you determine, you know, what is the residue modulo 3. Okay, so the logic is like this. You could have the number could be either residue 0 mod 3 or 1 mod 3 or 2 mod 3. Only 3 cases are possible. If it is residue 1 mod 3, then it's of the form 3x plus 1, and then when I get a 0 in the as a last binary digit, it's equivalent to multiplication by 2 of the previous number. Okay, so meaning, for example, if I have 101, which is 5, and I get 1010, it becomes 10, right? And if you get a 1 in the end, it's equivalent to multiplication by 2 plus the addition of 1, right? So if you have 101, which is 5, and now you add a 1 in the end, you get 1011, and 1011 is 11. Okay, if you get a 0, then what happens? If the number is residue 1 mod 3, then you would multiply by 2. If you get a 0, and you'll end up with 6x plus 2, which is of the form 3y plus 2 for some integer y, because 2x is also an integer, x is an integer, 2x is also an integer, right? Y equal to 2x, right? So this becomes residue 2 modulo 3. And similarly you can work out for the other cases. You can just, I have written it here and you can verify yourself, right? If you multiply by 2 for 0 mod 3, you get 0 mod 3, and if you multiply by 2 for 2 mod 3, you will get 1 mod 3, right? And similarly for an addition of a 1 in the end, if you append a 1 in the end to the binary sequence, then you get this, right? If you have 1 modulo 3, if you have a 0 modulo 3 and you add a binary 1 in the end, you will get 1 modulo 3. And if you have a 1 modulo 3 and you append a 1, you will end up getting 0 modulo 3, right? And if you have a 2 modulo 3 and you add a 1, you end up getting 2 modulo 3. So based on that, we can write down the Moore machine as follows, right? So this is the Moore machine. So whenever I have 0 modulo 3, I just emit 0, indicating that the number is 0 modulo 3. And whenever I have 1 modulo 3, I have to emit a 1, and whenever I have 2 modulo 3, I have to emit a 2, right? So this is how I can write down my Moore machine Q naught. See, Q naught on input 1, meaning 0 mod 3 on input, on getting a 1 will go to 1 mod 3, right? And similarly, you can just verify it yourself, right? So the state emits 0, 1 or 2, right? Because this corresponds to 0 mod 3, this corresponds to 1 mod 3, and this corresponds to 2 mod 3, right? So the state emits the 0, 1, 2 sequence, okay? And here for a Mealy machine, you could just take the 0, you know, yeah, you could just take the 0 and put it on the arcs, right? You could just take the 0, put it here, take the 1 and put it there, take the 0 and put it there, right? And you get the corresponding Mealy machine, right? So always, a Moore machine can be trivially converted to a Mealy machine. You have to remember that the Moore machine can be trivially converted to a Mealy machine, but the reverse is not true, right? So let me give you a little bit more detail on that. See, in this case, for complementing a binary number, you could get a more Mealy machine by just taking the zeros on the arcs, right? You take the 0 here, say /0, you take the 0 and put a /0 here, and you take the 1 and put a /1, and you take the 1 and put a /1 here, you get a corresponding Mealy machine. But it's not concise, right? You could do better with just one state, okay, in this case. Whereas in these cases, it turns out that it's not possible to reduce the number of states for Mealy machine, okay. The reason being, you have to look at the input transitions coming into all these states, right? See, in this case, so I'm talking about Mealy to Moore conversion, right? So you take Q naught here, all the input arcs coming into Q naught, they have anyway output 0, so that 0 could be taken inside. For Q1, again, all the input arcs, they have 0, so as output, so you could take the 0 inside. And again for Q2, all the input arcs have a 0 output, so that 0 could be taken inside the state, right? And the same holds even for this particular case, right? But here, now we have a problem. You look at the Moore machine and you take the input arcs coming in. I'm sorry. Yeah, this Mealy, we are talking about Mealy to Moore machine, right? So you look at the input arcs coming in. One of them takes in a 0 and emits a 1, and the other one takes in a 1 and emits a 0. So the outputs are not the same, right? So in this case, you could not just convert, it turns out that the Mealy machine and the Moore machine will have different number of states, right? So let us stop here, and now the conversion from Moore to Mealy and Mealy to Moore, we will look at it in the next video clip. Thanks for watching.